Welcome back to the deep dive. Most people probably think of a huge industrial motor as having just two settings, on and off.
Yeah, a big green button and a big red button.
Exactly. But when you're dealing with massive cranes or these incredibly complex assembly lines, well, simply starting and stopping just isn't enough. You need real choreography.
That's absolutely right. And today we're moving way beyond that simple start-stop button. We're going to be looking at the advanced control schemes. I mean, the dedicated circuits and all the protective mechanisms that let this huge machinery be reversed safely or moved by tiny little increments.
Timed perfectly, brought to a dead stop.
Instantly, yeah.
So, we've got a stack of instructional materials here, all designed for electricians. Our mission is to really decode the core physics and the engineering logic behind these special functions. Reversing, jogging, timing, and braking.
And we want to give you the language to understand the critical difference between, say, a technique like plugging and a more controlled approach like dynamic braking.
Okay, let's unpack this. I think we should start with probably the most fundamental maneuver after start, which is directional control.
Right. So if you're running a three-phase motor, reversing the direction is all about reversing the phase sequence. Electrically speaking, you swap any two of the three lines that supply power to the stator windings.
And that's it. That's all it takes.
That's the only way to change the direction of that rotating magnetic field.
So that implies we need two complete starting setups, right? One contactor for forward and another one for reverse.
Exactly. And they're interconnected. The whole setup is called a reversing motor starter. And crucially, while you have those two contactors, they have to feed into a single overload relay.
Why just one?
Well, because the motor's full load current is going to be the same whether it's running forward or reverse. So you only need that one point of thermal protection for the motor itself.
Okay, this is where the complexity and I imagine the safety requirements just skyrocket. What happens if somehow you manage to close the forward contactor and the reverse contactor at the exact same time?
Immediate disaster. I mean, you've just taken two different phases, let's say L1 and L3, and connected them directly together,
That's a direct short circuit.
a dead short. Right across the line voltage. It'll result in massive current flow, tripped main breakers, maybe even equipment damage. And this is why we have to rely on what the source calls the interlock imperative.
So you need redundant safety, and the first one is the mechanical interlock.
Yes, the mechanical interlock is a physical device. It's built right into the starter assembly, and it makes it physically impossible for both of those contactor armatures to pull in at the same time.
So if one is closed, a little bar or something literally prevents the other one from closing.
That's it. But the source material makes a really strong case the mechanical interlocks aren't enough on their own.
Why not? I mean, if it's physically stopped, what's the problem?
That's where the electrical interlocks come in. So even if that mechanical device stops the armature from closing its contacts, if an operator presses both buttons, both coils get energized. And the coil that's being blocked mechanically is still drawing a huge amount of stalled current. It's going to overheat and burn out very, very quickly.
Okay, so the electrical interlock protects the components themselves, not just the power lines. You're using a normally closed auxiliary contact from, say, the forward contactor.
And you wire that in series with the coil of the reverse contactor. Precisely.
So if the forward coil is on, its normally closed contact opens up.
And it guarantees the reverse coil cannot get power no matter what the operator is doing with the push buttons. It is an absolutely essential layer of fail-safe protection.
This detail leads to a really interesting distinction in standards. For people specifying equipment, the difference between NEMA and IEC starters really matters here.
Oh, it does. NEMA starters, which are really common in North America, they generally come pre-assembled and pre-wired with all these interlocks already integrated.
Sort of ready to go out of the box.
Pretty much. IEC starters, on the other hand, which are more modular and used globally, they typically supply the components separately. You get the contactors, the mechanical interlocks, the jumper bars, and the electrician has to assemble and wire those interlocks in the field.
So it's a choice between, what, simplicity versus customization.
Oh, got it.
Okay, let's talk about precise movement. Sometimes you don't want the motor to run for an hour. You just want to move a crane hook, like 2 inches. This is where we get into jogging and inching. What's the technical difference between those two terms?
That's a great question. They get mixed up all the time. Both describe energizing the motor for just a short little burst to move equipment a short distance. The key differentiator is voltage.
Okay.
Jogging happens at the motor's rated voltage. Full power, full speed, just for a moment. Inching is the same idea, but it happens at reduced voltage.
So how do you achieve that reduced voltage for inching? It's not like you just put a dimmer switch on a massive motor.
No, absolutely not. Inching usually leverages components you'd find in reduced voltage starting methods. You might use an autotransformer or a primary resistor, something like that.
And those devices temporarily drop the voltage.
Right, and that gives you lower torque and a much slower, much more controlled movement than a full voltage jog.
That makes the distinction really clear. But whether you're jogging or inching, the main control challenge is defeating that holding circuit.
That is the absolute technical hurdle.
Hmm.
Normally, the second you press start, the motor contactor closes and an auxiliary contact closes to form a holding circuit. It stays on even when you let go of the button.
But for jogging, you have to break that circuit.
You have to temporarily open it or defeat it so the motor stops the instant you release that momentary jog button.
The instructional materials have this very specific safety warning about this, though. They say a simple push-button setup isn't enough for what they call positive jogging. Why is that?
It's because of that critical break before make timing in the button. If you use a single button and you release it too quickly, the normally closed contacts of the button can actually reclose before the motor coil has fully de-energized.
And it just keeps running.
It stays energized and runs away. It's a really dangerous situation where the operator expects a stop but gets a continuous run.
So you need positive jogging, a guarantee that it's going to stop.
Exactly. The guaranteed safe methods involve either a selector switch or a control relay. In both cases, a dedicated mechanism, the switch set to jog or a relay energized by the jog button, is wired to permanently open the holding contacts.
So while you're in jog mode, there is physically no holding circuit possible.
None. The motor will stop when that button is released.
Now, if we connect this to the bigger picture, all of this starting and stopping, this jogging under full voltage, it must be just brutal on the electrical components.
It is intensely demanding. Jogging causes extremely frequent inrush currents. Just imagine the magnetic forces, the heat, the arcings, every single time those contacts slam shut.
It's got to reduce the life of the starter.
Drastically.
So if a NEMA Size 3 starter is rated for a motor under continuous duty, what happens if we put it on a heavy jogging application?
You have to oversize it. The NEMA sizing rule says a starter for jogging must be 1 NEMA size larger than what you'd need for continuous duty.
So that 25 horsepower motor needing a size 3 now needs a NEMA size 4.
Correct. Just to withstand that jogging duty cycle.
And what about for IEC-rated systems? They use different classifications.
For IEC, you look for the AC4 rating. That specific rating is for contactors designed to handle the high demands of plugging and jogging duty on squirrel cage motors.
That's a fantastic transition because often jogging those short bursts are just a lead-in to fully automated sequencing. Which brings us to our next segment, the timekeepers.
Automation depends entirely on reliable time. And we really have two main categories of timing devices. You've got your bulkier timing switches.
These mechanical ones.
Yeah, mechanical or sometimes large electronic units. They're for long cycles, like 24-hour or 7-day cycles for, security lights. But the precision work, that's done by timing relays.
Relays are the workhorses here. They're smaller, they're electronic, they're customizable, and they can operate from milliseconds up to hours. The guides break this down into 5 common timing functions. I think we should walk through the logic here because this is where people can get confused.
Let's do it. We'll start with the most common, TDOE, time delay on energization. It's also called an on-delay timer. The timing starts the instant the relay coil is energized.
Okay, clock starts ticking.
Right. But the contacts only change state after the set time has passed.
So the coil is on, but the action waits.
Correct. The classic example is sequenced motor starting. You've got 3 huge motors. You energize the TDOE from motor 2, and it waits, say, 5 seconds before starting, which reduces the massive combined inrush current that would hit your power supply.
Smart. Okay, next up is the tricky one. TDOD, time delay on de-energization, off delay. So here, the contacts change state immediately when they're energized, but the timing only begins when the relay is de-energized. That just sounds counterintuitive. Why delay after you turn the power off?
It's all about coasting or cooling. Imagine a big ventilation fan in a factory. The main machine shuts off, so the TDOD coil loses its power.
Okay.
But the fan motor keeps running for another 3 minutes. It's keeping the contacts in their delayed state to clear out residual heat or fumes. Then, after 3 minutes, the contacts revert and the fan shuts down. The delay happens after the input signal is gone.
Okay, that makes perfect sense in that context. Then we have interval timing.
Interval timing is for short, immediate bursts, Timing begins right when it's energized. Contacts change state immediately, but they go back to their normal state as soon as the time is up, even if the coil is still energized.
So if you power the coil for 10 minutes, but the interval is set for 30 seconds, the action only happens for the first 30 seconds.
Precisely. You could use it to sound a warning horn for 10 seconds, right when a huge conveyor starts. But you don't want the horn blaring the entire time the conveyor is running.
And one-shot timing sounds really similar, but it has this lockout feature.
It does. It also delivers a fixed burst of time after you press a button, but its critical feature is you cannot restart the cycle until the previous one is completely finished and the timer has reset.
Ah, the grocery store checkout conveyor belt?
That is the perfect example. You press the button, it runs for 5 seconds, then it stops. Mashing a button does nothing until that 5-second cycle is completely over.
And finally, the repeat cycle timer.
That's your flasher. An alternating on-off cycle, used for hazard lights, warning indicators, or any process that needs a constant repetition of on and off.
And we see these timers used directly in motor control, right? Like with a Y delta starter.
That is one of those elegant applications. The motor starts in the Y configuration, which gives it reduced voltage down by the square root of 3 to limit that inrush current. A TDOE timer is set.
And once the motor gets up to speed,
The timer trips, automatically disconnects the Y contacts, and engages the delta contacts, applying full voltage. It manages that whole transition automatically and very reliably.
so we can control direction, distance, and sequence. Now for the final piece, stopping power. How do we bring tons of rotating machinery to a fast, reliable stop? And sometimes even lock it in place.
But we have to rely on mechanical friction brakes and the various forms of electrical braking, often called dynamic or magnetic braking.
Let's clarify the mechanical brakes first. That power on versus power off distinction seems huge.
It's absolutely vital. A power-on brake is energized to apply the braking force. So if you lose power, the brake is released. Not good for safety.
Not fail-safe.
Not at all. The fail-safe system is the power-off brake. This brake uses powerful springs to apply the brake shoe, so it's always on by default. You have to apply power to a solenoid to release the spring pressure and let the motor turn.
So if the power is lost,
The spring instantly clamps down, the machine stops, and rotation is locked.
that's non-negotiable for things like hoists or elevators. Loss of power must mean a dead stop.
Precisely. Now, electrically, we use dynamic braking. We're harnessing the motor's own inertia. You reconfigure it to act as a generator, creating magnetic counter-torque.
How does that work for a DC motor?
With DC, you disconnect the supply, and you instantly connect a big braking resistor across the armature. The spinning armature, which is still excited by the field windings, generates voltage, and that current flowing through the resistor turns rotational energy into heat.
And that stops it. So a smaller resistor means a faster stop.
Smaller resistance, more current, stronger braking. Exactly.
And for AC induction motors, we use something called injection braking.
This is a really clever use of power. You de-energize the AC, and then you briefly inject a DC voltage into the stator windings.
DC into an AC motor.
Right. That DC creates a static, non-rotating magnetic field. As the AC rotor coasts through this static field, massive currents are induced in the rotor bars, and that generates an extremely powerful opposing torque. It brings the motor to a very rapid stop.
That sounds significantly more elegant than the brute force method. Plugging.
Plugging is the electrical equivalent of throwing your car into reverse while you're still doing 60 on the highway.
That's a great way to put it.
It is the sudden and full reversal of the phase sequence while the motor is still running in the opposite direction. It stops the motor incredibly fast, but at a huge cost. It generates enormous amounts of heat and current spikes far, far higher than even normal starting current.
I can't imagine the motor windings or the contactors like that very much.
They do not. It's a trade-off for speed.
So if you do initiate plugging, how do you make sure the motor actually stops and doesn't just immediately take off in reverse?
You have to use a control device, usually a centrifugal switch, a plugging switch mounted on the motor shaft. When you hit the plug control, the reverse contactor energizes. The motor slows, but the switch stays closed, keeping that reverse contactor energized.
Little.
Only once the motor slows down almost to a stop does the centrifugal switch reopen, instantly de-energizing the reverse contactor.
And if a particular machine, like a fragile conveyor, just cannot tolerate that sudden reversal at all, you'd use an anti-plugging circuit.
That's the guardrail. The anti-plugging switch makes sure the opposite direction contactor cannot be energized until the motor has slowed or stopped entirely. Its contacts open when rotation starts, and they only reclose when the rotation is almost zero, preventing that sudden damaging reversal.
We've covered such essential specialized knowledge today, from the layers of mechanical and electrical interlocks that make reversing safe, to defining the precise differences between jogging and inching.
And why you have to oversize your NEMA starters for those high-wear applications.
Right. And we've detailed the critical differences in contrasting the absolute safety of a power-off brake with the aggressive, high-wear dynamics of injection braking and plugging.
These circuits really are the unsung heroes that make all this industrial reliability even possible.
So here's a final provocative thought for you to chew on. Traditional motor control relies on these high-wear components and brute force current spikes to do these specialized moves, jogging, plugging, timing transitions. But we know now that modern variable frequency drives, VFDs, can do all of this electronically and softly. They can achieve custom inching, dynamic braking, sequence starts, all inside the drive itself. If we accept that plugging causes massive component wear and dynamic braking needs extra circuits, what does the growing reliance on VFDs tell us about the industry's fundamental shift away from these high-maintenance traditional controls toward high-capital electronic control? You now have the language to weigh those maintenance costs against the initial investment.